Hello, and welcome to a deep dive into one of the most elegant and powerful principles in all of science and engineering. Today, we're not just going to learn about Kirchhoff's voltage law, we are going to master it. We're going to explore its history, unpack the beautiful physics behind it, and learn how to apply it like a professional. By the end of this session, you'll see that KVL isn't just a rule to memorize, it's a fundamental truth about how our universe works. So, let's begin with the man himself. In the mid-1840s, a brilliant young Prussian physicist named Gustav Kirchhoff was studying the flow of electricity. At the time, scientists were just beginning to understand circuits, and they needed a reliable way to analyze them. Building on the work of George Ohm, Kirchhoff formulated two simple, yet profound, laws that became the bedrock of circuit analysis. Today, we focus on the second of these, the law of voltages. The formal statement, as you see it here, is, the algebraic sum of all voltages around any closed loop in a circuit is equal to zero. Now, let's treat that sentence not as a definition to be memorized, but as a treasure map. Every word is a clue leading us to a deeper understanding. The two most important clues are voltage and closed loop. To truly grasp KVL, we must first have a rock-solid understanding of what voltage really is. We often use analogies, like water pressure or the height on a hill, and those are fantastic starting points. But let's go one level deeper. Voltage is, more formally, electric potential difference. It's a measure of the potential energy that an electric charge has, simply because of its position in an electric field. Imagine you're lifting a bowling ball off the ground. You have to do work against gravity to lift it. In doing so, you give that ball potential energy. The higher you lift it, the more potential energy it has. If you let it go, that stored energy is converted into kinetic energy as it falls. Electricity works in a remarkably similar way. A battery, for instance, creates an electric field. When it moves a positive charge from its negative terminal to its positive terminal, it's doing work, like you lifting that bowling ball. It gives that charge electrical potential energy. The amount of energy it gives per unit of charge is what we call voltage. 1 volt literally means 1 joule of energy per 1 coulomb of charge. This brings us to the most fundamental reason why KVL works. The electric field inside a circuit is a conservative field. That's a fancy term for a very simple idea. In a conservative field, like gravity or an electric field, the total energy change in moving from a starting point to an ending point depends only on those 2 points, not on the path you take to get there. If you hike from the base of a mountain to its peak, you gain a certain amount of potential energy. It doesn't matter if you took the short, steep path or the long, winding path. The change in your elevation, your potential energy, is exactly the same. And here's the crucial part: if your starting point and your ending point are the same place, if you start at a cabin, hike all day, and return to that same cabin, your net change in potential energy must be, by definition, zero. You are at the same elevation you started at. This is Kirchhoff's voltage law in a nutshell. A closed loop in a circuit is a journey that starts and ends at the exact same point. Therefore, the sum of all the potential energy changes, the voltage rises and the voltage drops, along the complete journey must equal zero. The books must balance. Now, let's look at the players in our circuit who create these changes. First, we have the sources of voltage, the components that provide a voltage rise. These are our energy providers. The most common example is a battery. A battery is like an energy pump. Through a chemical reaction, it takes charges at a low potential energy and pumps them up to a high potential energy. When we move across a battery from the negative terminal to the positive terminal, we are gaining potential. It's an uphill climb. Then, we have the components that cause a voltage drop. These are the energy consumers, often called loads. Resistors are the classic example. A resistor is a material that impedes the flow of electrons. As the charges are pushed through the resistor, they collide with the atoms of the material, and their electrical potential energy is converted into another form, primarily heat. This loss of potential energy is the voltage drop. It's the downhill portion of our journey. Lights, motors, and speakers are also loads that create voltage drops, converting electrical energy into light, motion, and sound. This leads us to a critical concept for applying KVL correctly: sign convention. To make our algebraic sum work, we need a consistent way to assign positive and negative signs. The standard method is the passive sign convention. It works like this. When you trace your path around the loop, if you cross a component in the voltage drops, like going from a plus sign to a minus sign on a resistor, you subtract that voltage. It's a negative change. If you cross a component and the voltage rises, like going from a minus sign to a plus sign on a battery, you add that voltage. It's a positive change. Let's apply this to our simple example circuit. It has one voltage source, V_S, and three resistors, R, R2, and R3. Let's decide to walk around this loop in a clockwise direction, following the blue arrow. We can start anywhere, so let's pick the bottom left corner, right before the battery. First, our first move is crossing the battery, V_S. We go from the negative terminal to the positive terminal. That is a voltage rise. So, we write it down as plus V_S. Second, we continue clockwise, up to resistor R_1. The current flows from the positive side to the negative side, so crossing it in this direction is a voltage drop. We write minus V_1. Third, next is resistor R_2. Same story. We cross from plus to minus, so it's a drop. We write minus V_2. Finally, we cross resistor R_3. Once again, from plus to minus, a drop. We write minus V_3. We have now returned to our starting point. We've completed the loop. KVL tells us that the sum of all these must be 0. So our equation is plus V_S minus V_1 minus V_2 minus V_3 equals 0. This is the mathematical statement of balance for this circuit. If we rearrange it by moving the drops to the other side, we get V_S equals V_1 plus V_2 plus V_3. This is the other popular form of KVL. The sum of the voltage rises equals the sum of the voltage drops. The energy pumped in by the source is completely consumed by the three loads. Now, a common question is, what happens if I trace the loop in the other direction? Let's prove that it doesn't matter, as long as we are consistent. Let's start at the same point, the bottom left corner, but this time, we'll walk counterclockwise. First, our first move is crossing resistor R_3, but this time we're going from its negative side to its positive side. This is going uphill against the drop, so we see it as a rise. We write plus V_3. Next, we cross R_2 from negative to positive. Another rise. We write plus V_2. Then, we cross R_1 from negative to positive. One more rise. We write plus V_1. Finally, we cross the battery V_S, but this time we're going from its positive terminal to its negative terminal. We are going downhill on our energy pump, so this is a drop. We write minus V_S. We're back at the start. Our new equation is plus V_3 plus V_2 plus V_1 minus V_S equals 0. Now, look at this equation. If we move the minus V_S to the other side, we get V_1 plus V_2 plus V_3 equals V_S. This is the exact same result we got before. The direction you choose is irrelevant. The fundamental physics of balance holds true no matter how you look at it. Now, let's level up. Real circuits often have more than one loop. KVL is the tool we use to solve them. This method is often called mesh analysis. Let's imagine a slightly more complex circuit, perhaps with two loops sharing a central component. For example, a battery V_A on the left loop, a battery V_B on the right loop, and a resistor R_C in the middle, shared by both loops. To solve this, we define a current for each loop, say I_1 for the left loop and I_2 for the right loop, both flowing clockwise. Then we apply KVL to each loop independently. For loop 1, the left loop, we would start, say, at the bottom. We'd have a rise from the battery V_A. We'd have a drop across a resistor R_A that's only in the left loop. Then we get to the shared resistor, R_C. This is the interesting part. The voltage drop across R_C is caused by two currents. The current from its own loop, I_1, is flowing down through it. But the current from the other loop, I_2, is flowing up through it. So the net current determines the drop. Our KVL equation for loop 1 would look something like plus V sub A minus the drop across or sub A minus the drop across or sub C equals 0. For loop 2, the right loop, we do the same thing. We'd see a drop from battery V sub B, if we're going clockwise and hit the positive terminal first, a drop across a resistor or sub B only in the right loop, and then another drop across the shared resistor or sub C, again considering the effects of both I sub 1 and I sub 2. What we end up with is a system of two equations with two unknowns, I sub 1 and I sub 2. And using algebra, we can solve for both currents. This is the power of KVL. It allows us to take a complex, interconnected circuit and break it down into a set of simple algebraic equations that we can solve. Finally, let's talk about the ultimate partnership in circuit analysis, KVL and Ohm's law. Ohm's law states that V equals I times R, or voltage equals current times resistance. This is the key that unlocks our KVL equations. Remember our first equation, V sub S minus V sub 1 minus V sub 2 minus V sub 3 equals 0. We know what V sub 1, V sub 2, and V sub 3 are. They are the voltage drops across the resistors. According to Ohm's law, the voltage drop across a resistor is the current flowing through it multiplied by its resistance. Since this is a simple single-loop circuit, the same current, I, flows through everything. So we can substitute. V sub 1 becomes I times or sub 1. V sub 2 becomes I times or sub 2. V sub 3 becomes I times or sub 3. Our KVL equation now transforms into V sub S minus I times or sub 1 minus I times or sub 2 minus I times or sub 3 equals 0. Look at what we've just done. If we know the voltage of our battery and the values of our three resistors, we have an equation with only one unknown, the current I. We can easily solve for the current flowing in the circuit. This is how these laws work together to give us a complete picture of the circuit's behavior. So let's bring it all home. Kirchhoff's voltage law is not just an arbitrary rule. It is a direct consequence of the conservation of energy. It tells us that in any closed electrical journey, you must end up with the same potential energy you started with. The energy provided by the sources must be perfectly balanced by the energy consumed by the loads. We've seen how to apply it using a consistent sign convention, how it works regardless of the direction you trace the loop, how it can be used to analyze complex, multi-loop circuits, and how it partners with Ohm's law to solve for unknown currents. It is a simple, elegant, and profoundly powerful tool. It's a statement of perfect balance, written in the language of electricity. Thank you for taking this deep dive with me today. I hope you now have a firm, intuitive, and practical mastery of KVL. If this comprehensive guide has been valuable to you, please consider liking and subscribing for more explorations into the fascinating world of science and engineering. Until next time, stay curious.